we know that if I exert a force on this ball, the ball is going to accelerate and therefore its speed will change, its velocity will change, right? So we know that. Now, two very big scientists around the time that Isaac Newton was there was also a big scientist called Leibniz in Germany, and they always kept arguing about what was the important characteristic of force. Because I know that I am exerting a force, it produces an acceleration, but if you wait for some time, then force and the time that you are waiting together, they somehow seem to change the velocity. That was Newton's argument. So Newton said what was important was force into time. He called this quantity impulse, and today we use the symbol J to talk about impulse. So this is impulse of a force. So what is impulse? It is force into time. And while Newton said this is the most important thing, this is the only thing that matters, Leibniz, sitting in another country, little further away from Newton, was arguing heavily about this, saying, see, you are getting a vector quantity, force into time is a vector, and that's not a good point that's not a useful thing. What you should be using is force into displacement. So to make it a scalar quantity, he obviously didn't know about dot products at that point, but he defined it somewhat like this, and he called this work. Okay, so this idea that you are going to talk about force and displacement. So it is not how much force is acting, but how much is it acting over, what distance is it taking this fellow. Here Newton is saying that doesn't matter, how far away it moves doesn't matter, what matters is how long does it act. Is it acting for 2 seconds, 5 seconds, 10 seconds? Newton's argument was time matters. It does matter. Leibniz's argument was displacement of the object matters. Let us think about why both of these people were arguing this, and there is some reason behind both, and it turns out today we know that both have a valid point of view. This is also an important quantity, this is also an important quantity. But at that time, of course, Newton was very powerful, so he basically told everybody to ignore Leibniz, and basically for a while, for about almost 100 years or so, people focused on impulse as the most important quantity that force produces. Okay, the effect of the force you think in terms of impulse. It is important, nothing wrong with it. But it turns out that this is not just equally important, sometimes I would even argue that it is even more important. That's not true. This is equally important. Both are equally important. Okay, work turns out to be an extremely important quantity. Impulse also turns out to be an extremely important quantity. So force produces impulse when you do force into time. Force produces work when you have a displacement. Let us think about that. Why displacement? Because if I look at this ball and if I have a force acting and the ball doesn't move, like for example, suppose the ball was there and I kept exerting a force, I am not making this ball gain any kind of velocity. You might argue, well, that is because there is another force from that direction. But in general, if I want this ball to gain speed, what happens? I have to push it, and if it's already moving in that direction, I keep pushing it, it will become faster and faster. Now imagine a ball that was coming like this, which had already a velocity. Then when I exert a force like this, the speed comes down, it slows down, right? So if it is moving this way and I push in the same direction, the object speeds up. That is, its displacement and force are in the same direction. I am adding to its what we call energy. Okay, so work is very closely related to this idea of energy. So I will first talk about kinetic energy. At Leibniz's time, it was just called energy. Okay, and it turns out to be half mv square. You know this already, right? Mass into speed square by 2, half mv square is the kinetic energy of that particle. You have a related idea here, and that idea is called momentum. So work and kinetic energy are very closely connected. Impulse and momentum are very closely connected. So momentum, what is momentum? It is mass into the velocity, not speed. Kinetic energy is half into m into speed square. Leibniz's argument was, let us deal with scalar quantities. So all of these are scalar quantities. Newton, of course, was a big fan of vector quantities. So Newton's way of doing things was always, let us do it with a particular direction in mind. So impulse is force into time. Momentum is mass into velocity, not speed, velocity. The symbol for this is P. So we usually write P with an arrow on top to say momentum. Okay. Symbol for impulse is J. Why can't I use I? Turns out I is used in many other places. So therefore we use J for impulse. Work of course is W, that's a simple symbol. And for kinetic energy we'll just use KE. Okay, so these symbols are easy. And you should remember that work and kinetic energy both are scalar quantities, whereas impulse and momentum both are vector quantities. Why are these fellows arguing about the importance of this? And why are these two connected? Very simple. If you take Newton's laws, basically what does Newton's law say? F is m times A. A is V minus U, and by the way these are vectors, by T. So what Newton did was to take this T up there, and its argument was F into T makes mu into mv. So it changes mu into mv. So mv, the quantity that is changing, this quantity is what he called, in fact he called it the quantity of motion. He called it momentum. Today we call it momentum. Newton called it quantity of motion. So this is impulse, right? F into T is impulse, changes momentum. So we'll say final momentum minus initial momentum. P stands for momentum, P as a vector. We will later use P for power, okay, but power is different, momentum is different. So this is momentum with a vector, always with an arrow on top. So is that clear? So all we are doing is to say V minus U by T is acceleration. So mv minus mu is F into T. We are dealing right now with only constant forces. So all of this is for constant force. Later we will come back and look at what happens when we have variable forces. So for constant forces, let us see, force is mass into acceleration, Newton's second law. Just bring it here and you have got mv minus mu. Newton obviously would start with Newton's second law. What else do you expect Newton to start with? So therefore this idea that impulse changes momentum, we write this change in momentum like this, delta P. So change is always final minus initial. So change in momentum is impulse. So impulse produces change in momentum. That was something Newton kept arguing. Right? He said that is what you should focus on. Don't worry about force. Worry about force into time, but because force into time will change the momentum of the object, mass into velocity. Now Leibniz came back and said, no, listen, Galileo had another equation. What is Galileo's equation? V square minus U square is 2 times AS. So we'll just write AS here and bring the 2 down here. And if I multiply by m, I am going to get m times AS is m times V square minus m times U square. Now this MA, what is that MA? Force. So this is force times displacement is, what is this? Kinetic energy final minus kinetic energy initial. So we'll write this as change in kinetic energy. He said just like that there is an impulse to momentum equation, there is a work to kinetic energy equation. So he said that is very important. And it turns out that this is a statement that we have written in a very, very weak way. If A was pointing up and S is down, you know that you have to put minus signs and so on. But if A was pointing like that and S was like that, this would have been a dot product. So actual statement, Galileo's statement, we should have written like this. V square minus U square is 2AS. Actually turns out to be V dot V minus U dot U is 2 times A dot S. You can see that this is the same statement as that, right? Now with this definition, you can see that A dot S, this is not a definition, with this way of writing it, you can see that this should also be F dot S. So if F and S are in the same direction, F dot S turns out to be positive. If F and S are in the opposite direction, it turns out to be negative. And if F and S are in perpendicular direction, this force does not change speed. You might have seen that in circular motion, right? If you take a ball and go around, then let me show you. So if I take this ball and I make it go around like that, right? So it's going in a circle, and if you see, this is the direction of the velocity. Everywhere the velocity keeps changing. Now if you took the force, there is a force like that, there is a force like that, etc. But overall, if you try to look at the net force and say that the net force acts in this direction, the net force is acting perpendicular to the velocity. So when that happens, then you find that the speed does not change. Okay, so we will see this again and again, that when F and S are perpendicular, that does not change the kinetic energy of the object. For Leibniz, this was a very important point, that F and S are in the same direction, speed increases. F and S are in opposite direction, speed decreases. F and S are perpendicular, speed doesn't change. And what if it was like this? Then you say F into S into cos of the angle. It's a dot product. So you say F into S into cos of the angle between F and S. So he defined, in some sense, work like that. You can understand work and the basic idea behind it quite well. For example, if I had a big huge mass and I wanted to lift it up. If I lift it up from the ground to the table, I'll be doing some amount of work. But if I have to lift it from the ground some 5 floors up, am I doing more work or less work? Clearly I'm doing more work, right? Right? So basically it is not just the fact that I'm exerting a force, I may have to exert the same force, but now I have to take it through a much larger distance. So work basically is the product of force and the displacement, and that tells you how much energy you have transferred. Of course it's a definition, so we'll have to learn how to use it. But the main thing I want you to keep in mind, this statement that we have written here, we'll come back to it later and show that this is a much more valid statement across many more situations. But at least for constant force, we have now seen that work changes kinetic energy. So the work done is basically force dot displacement. So this is the definition of work done by a force. So what is the definition? Force dot displacement, or force into displacement into cos of the angle between force and displacement. One of the reasons why we use dot product, learn dot product, is so that work calculation becomes easy. So I hope this is clear. First point, impulse is a vector, work is a scalar quantity. Momentum is a vector quantity, kinetic energy is a scalar quantity. Impulse changes momentum. Work, this is W, work changes kinetic energy. So I hope that is clear. Now let us look at this block. So this block is a 5 kg block in space, and there's a force of 10 Newton acting. It already has a velocity of 4 meters per second. And it's a very simple question. So the block moves there. In 3 seconds, we want to know various quantities and calculate what happened. Now, very simple thing is that A, how much is the acceleration? Force divided by mass, so 2 meters per second square. AT is 6, right? And now, so U plus AT will tell me the velocity there must be 6 plus 4, so 10 meters per second. Right? So this is 6 plus 4, 10 meters per second. So I know the velocity there is 10 meters per second. The mass, of course, continues to be 5 kg. Let us quickly use this to calculate various things and check if all our stuff should be correct. Now what about the impulse? Now I know that the force is 10 newtons. It is acting for 3 seconds. So the impulse is very simple. 10 into 3, 30 Newton second. So that is the unit. And the direction is the same as the direction of the force. This has to have a direction. Let's say I cap direction. What about the initial momentum? Mass into velocity. So 5 into 4, 20. Now the units, you can think in terms of Newton second, but usually people write kilogram meter per second. But this and that are the same units, because kilogram meter per second square would have been Newton into second. 1 second would have got cancelled. So it is the same thing in that direction. And what about the final momentum? Well, it is 5 times 10, so it is 50 kilogram meter per second in that direction. Can you see that final minus initial momentum? So delta P is 50 minus 20, which is 30, and that is equal to the impulse. So hopefully that's clear, right? So now if I try to do the same thing with work, now the problem here is calculating work, I need to know the displacement. But I can calculate kinetic energy because I do know the speed. So let us first finish this, then we will come to work. But what is the kinetic energy final? Half into m into v square. V square is 10 square 100. And so if I cancel that, that's going to give me 50 times 5, 250 joules. The unit for kinetic energy and work and all forms of energy is joules. Should I put an arrow? Should I say that it's in that direction? No, it's a scalar quantity. Kinetic energy, no direction. It is just a number, 250 joules. Kinetic energy initial, half into mass 5 into 4 square. 4 square is 16, 16 by 2 is 8, 8 5s are 40. So I know my work must be how much? My work must be 250 minus 40, which is how much? Which is 210. It should be 210. I already know that answer. But work must be force times displacement. I know my force is 10. So that means my displacement must be how much? 21 meters. But let's calculate the displacement. You know that S is equal to ut plus half at square. Ut, so 4 into 3 plus half a into t square. And so this is 9. How much is this? 12. 12 plus 9 is 21. So it is indeed 21 meters. So you get 210 joules. Okay. So force times displacement. In this case, force and displacement both are in the same direction. It was a very simple question. This is just to kind of get started off on using work and energy and impulse and so on. Let us think about another way we could have done this. We could have done average velocity is 4 plus 10 by 2 because it's uniformly accelerated, and therefore we'll get 7. 7 times 3 is 21. That also gives you 21. So you know that force times displacement is work. And notice again that change in kinetic energy is equal to the work that was done. So this is a very simple, straightforward example. Now let us take another example where we have vectors and we want to calculate both impulse as well as work. So here there is a particle that starts at A and then ends up at B. So you know its displacement is given, it is 7I plus 2j. And there is a force, a constant force that is acting, which is 3I plus 4j. What is the work done by this force on that particle? So suppose I want that, it is just simply F dot S. So you can calculate that quite easily because it's just a dot product. So 3I plus 4j newtons dotted with 7I plus 2j. And you know how to calculate dot product. So the 3 into 7, 3 into 7 is 21 plus 4 times 2, so that is 8. And then the 3 times 2 won't matter because it's I dot j, which is 0, j dot I, which is 0. So this is just 21 plus 8, which is 29 joules. If we did everything in SI units, Newton meter, that is going to give us joules. Now if I want to calculate impulse, right, this j is different from that j, that's the j unit, joules. This is the j vector impulse. So impulse is very straightforward because this takes 4 seconds. It's given it takes 4 seconds. So it is just F into t. So it is 3I plus 4j times 4 seconds. And so that is 12I plus 16j Newton second. So that's clear. So this is a vector, that's a scalar quantity. But does it mean that the particle moves like this? If I have a force like this, is it possible that the particle moves like that? Yes, it is possible. If this was the only force, is it still possible? Yes, because you see I could have thrown it this way. If I take a ball and I throw it, the ball goes this way, right? The force is downwards. but the ball moves like that. There must be an initial velocity. So if this had an initial velocity u, and then this fellow goes like that, and it will have a velocity like that v. And because it has only one force and it's a constant force, it will have a constant acceleration. In that case, we can actually find out v minus u must be equal to at. So if I knew the mass, in some sense I can find from u I can find v, from v I can find u. This displacement is only telling you the displacement. It is not telling you the path it moves in. So work done is force times the displacement if it was a constant force. Right now we are talking about one single force and a constant force. Okay. What if it is not a constant force is something that we will study a little later. At this point I want you to just keep in mind how to calculate F dot S. So I hope this is a very simple idea, right? To find out work, you should be able to calculate work, you should be able to calculate impulse, and then you should also be able to match kinetic energy and work. And you should be able to match momentum and impulse. Okay.